Hello, my name is Jim Williams and I'm here in the lab at Linear Technology Corporation to talk to you today about low noise, high voltage DC to DC converters. And at this point a good question might be, who needs it? The answer is people doing primarily transducer signal conditioning. Transducers that need this low noise, high voltage include photomultipliers, which is of course for light, avalanche photodiodes, which is also of course for light, ultrasonic transducers, capacitance microphones, and radiation detectors. These all require high voltage, and any noise on the high voltage can masquerade as false signal coming out of the transducer, so it's highly undesirable. And what kind of numbers are we talking about? For low noise, typically you're going to want less than a millivolt in the high voltage output at 100 megahertz bandwidth, and anywhere from 100 to 1000 volts DC output. So this is high voltage, and typically you're coming up from a low voltage supply, 5 or 10 volts, hence DC to DC converter. The saving grace is the loads in these transducers are light. They run from units of microamps to an absolute maximum of about 5 milliamps. This low output current permits certain freedoms in the design of the converter, and I want to go over those in a cursory kind of way right now. One way to do the converter is to build a resonant sine wave producing power stage which drives an output stage, runs through a two-section filter, I'm going to come back to this in a minute, and feeds back to control the current through the sine wave resonant converter. That's one way to do it. You'll notice I've used a resistor here in the filter network instead of an inductor. Why? The fundamental reason is I can get away with a resistor because at 100 to 1000 volts out, a couple of volts drop is no big deal. And the resistor has much lower shunt capacitance across it than an inductor would. It makes a much better filter. And you can get away with that because the load currents are so small. One potential problem with this design is you're burning power in this linear control element. You could go to something like an LT1534, which is an edge time controlled switching regulator, which maintains low harmonic content in switch mode delivery drive to here. Another way to implement this converter is to push-pull pulse width modulate, get rid of the whole bottom end, edge time controlled. Similar to the last example, we modulate across a step-up transformer through the same resistively equipped filter network, down through the feedback network, and back to complete a control loop. What kind of performance do we get out of something like this? Let's go to the lab bench and take a look. Okay, I'm here at the lab bench. We're going to take a look at what we get for noise out of one of these converters. The converter I have selected is a minus 1000 volt converter designed for photomultiplier application. And I'll show you how we measure low noise. We go through a 40 dB low noise 200 megahertz preamp into the scope vertical and display on the tube. I'm measuring DC voltage on the voltmeter here. Right now the converter's off. I'm measuring my noise floor at quiescence. The noise floor of the test setup is about 100 microvolts peak to peak. Now I'm going to turn the converter on. The voltmeter indicates we're just below minus 1000 volts. And what we've got on the scope at 100 microvolts per division is about 100 microvolts peak to peak of noise, total harmonic content. What that means is I'm getting about 1 part in 10 million noise on the output of my 1000 volt converter. That's pretty low noise. We've covered a lot of ground today fairly quickly. You can get much more detail in LTC application notes AN 118 or AN 70, or for that matter, you can call me up on the telephone and ask me any question you want.